Hi there. So today I'm going to talk a bit about superposition and how it actually works, kind of like the nuts and bolts of how superposition runs. And the idea behind this is I get students who try to use the tables, who go to use the tables, and they're not quite sure what to do, right? So the general idea here is I've got this classic propped beam, as they call it, right? I've got a cantilever, distributed load. That by itself would be enough to support the load, the cantilever, I should say. But we've gone and added in a roller and made things a little bit more supported. And in the end, we actually reduced the moment a little bit too while we're at it, and reduce the load on the cantilever end. That's why we do it. But what we do then is if we were to try to figure out how the load was distributed, what the reactions are at the wall and at the roller, we draw this free body diagram or something like it. We come up with these loads and we solve equilibrium, and we come up with the sum of forces in X giving us no horizontal reaction at A, which we don't find surprising. It's the only force at A. We find that the two vertical reactions have to add up to the applied load WL. Well, that makes some sense too. In some moments, MA has to equal minus WL squared, or if you want to think the other way, By times L minus WL squared over 2. Okay, great, fine. We got too many unknowns, not enough equations, statically indeterminate. All good, nothing unexpected. And then this phrase in purple is what you keep seeing, right? Treat a support as redundant. What does that mean, though, right? What does that mean we actually wind up doing? And the answer, the way I think of it at least, the way that works for me, is that first, we remove a support and we replace it with the load that it supplies. Okay, load, and really nothing says I can't say loads, right? Because I could take away an entire cantilever. Sometimes I have, sometimes you have to. So this situation, the classic common thing to do when we have something that looks like this, is to turn it into something where I still have the cantilever. I decide to knock out that roller support, right? So instead of drawing a roller support on this, I'll draw in my force By. And then what we do is we enforce the boundary condition or conditions. So here comes that parentheses S again. And the boundary conditions that the support provides. Okay, so in this case, it's a roller. It has a force only. Forces counteract displacements or deflections. So therefore, we have to enforce artificially that VB equals 0. VB is going to be 0 for that case on the left with a circled roller anyway, right? What we have to do then is we have to provide a force, and the force that's provided is going to be the one that makes it so that the boundary condition is still met. Okay, so with that in mind then, we can say that VB, I'll keep it in green, it's equal to VB due to our distributed load. That was interesting, thank you, Word. It's VB due to our distributed load plus VB due to By, and that's got to be 0. And here's where you start looking stuff up in the tables, right? And I've got a table of deflection sitting just to my right here. It's the textbook that I'm using this semester, and it's a decent one. And it certainly has a load on the end of a beam, and it has a distributed load on the end of along a cantilever beam. So what we can say then, looking this up, VB due to the distributed load is minus W L to the 4th over ADI. That's the maximum deflection for that beam because, well, we're looking at the far end, which makes sense. It should be the most deflection. It should be the furthest away from the cantilever support after all. And we can say that VB due to BY is equal to positive BY L cubed over 3EI. Why positive? Because BY points up. It's that simple. Okay. So therefore, what we would say is minus WL fourth over 8EI plus BY, I should say, L cubed over 3EI equals 0. I do some quick mathematical manipulations. By the way, the EI's go away, the L cubed goes away. It looks to me like BY will be equal to 3/8 WL. So therefore, AY is 5/8 WL, and MA is minus WL squared over 8, because it's 3/8 WL times L minus WL squared over 2. 3/8, well, a half is 4/8, so therefore I wind up with minus 1/8. Okay. That's all well and good. And sure, that's the way superposition runs, and that's the way people normally use superposition, is they take away the roller support. I'm not going to do that the second time, though, right? We can do something else. What if we just remove the cantilever moment? Really? I mean, seriously, that's a redundant reaction too. It's an extra reaction. If I just had this thing here on the left with the cantilever and the roller, if I took away the cantilever and made it a pin instead, it would be statically determinate, wouldn't it? So I could treat that moment as being something that's extra, right? There's no reason I can't. So what we would say then is this situation gets turned into something a little bit more like this, with again the distributed load applied. And now, instead of the cantilever wall, I've got a pin. Therefore, the load the cantilever supplies that's above and beyond this pin has to be included as an external load. Well, hey, look, there's MA. And now I have to identify a boundary condition, right? I often abbreviate these BC, but I'm not going to do that now. My boundary condition, well, I had a cantilever at the wall. At the left, I had a wall. It's a cantilever. At that wall, at that left end, the moment causes a rotational sort of motion, right? So that means the moment has to supply a rotational kind of constraint. Rotation, angle, slope. The angle at the wall has to be 0. Okay, so if I look up in my handy dandy table, well, I'll look that up in a minute. First, let me break it down. Theta A is equal to theta A due to the moment plus theta A due to the distributed load, and of course that has to equal 0. Now let's go to my handy dandy table, because I got the two little parts of it, right? I've got the distributed load that's going to cause this to sag, right? Because there's no moment there anymore. There's no, if I just look at the distributed load by itself, I've got a pin instead of a cantilever, it is going to sag. The moment's going to cause the whole thing to rotate, though. So hopefully, well, not hopefully, the correct moment of MA that I get is going to be the one that makes this whole thing balance out to where I have no angle left. Interesting, huh? So what I see is that if I look up in my table, my theta A due to the moment is equal to minus ML over 3EI. And yes, I quite literally have the book right over there. Okay. My theta A due to the distributed load, I've got that equal to, there we go, minus WL cubed over 24 EI, that has to equal 0. Because I have 0 on the right-hand side, the EIs can go away. I can get rid of an L and an L here. And I can get the intermediate step, just to show it, that m over 3 is equal to minus WL squared over 24. And I think you might be seeing it by now. That's m sub a, not m. Let me make those both MAs, right? M sub a is equal to minus WL squared over 8. And here we are again. Would you look at that? It's the same thing we had up above, which means hopefully, if I go back into equilibrium, I had that MA was equal to BYL minus WL squared over 2, which then has to be equal to minus WL squared over 8. It looks like BY is equal to 3/8 WL, and sum of forces in Y, AY plus BY equals WL. AY is 5/8 WL, and we're done. Superposition works that way too. All we're doing, well, superposition works because we add things together. When we look at something using table cases for something that's statically indeterminate, this is more what I'm after. This is what people call beams via superposition. That's not what I'm after here, right? I don't like calling it that. This is beams using the table cases, okay? So what we're going to find is that we just have to knock out one of our reactions or more, depending on how many extra equations we need, replace them by the reaction force or moment that we had applied as an external load instead of as a reaction load. The reactions are external, so there's no real big difference there. And we have to enforce those conditions, those boundary conditions that those particular loads apply. Okay, in the case of a moment, angle is 0. In the case of a force, deflection is 0. And there we go. All right, enjoy. Thanks a lot.